Hi guys, today this video is going to be on introducing ice tables. Okay, so the two problems I'm going to set up and go through are the very bottom problem on 2.03 and the very top problem on 2.04. So if you have those two sheets, that would be a great resource as I go along through these problems that you can follow along with. So let me introduce a little bit about ice tables. So an ice table is an acronym, and it's a tool. Okay, so the acronym here is I stands for initial, C stands for change, and E stands for equilibrium. And essentially, why we use ice tables is to help us organize our information to solve problems that involve either weak acids or weak bases. More often than not, the types of problems that you'll solve are things like, what's the pH of a weak acid or a weak base? Okay? Or maybe they give you the pH and it says, hey, what's the Ka of that weak acid? Or what's the Kb of that weak base? These are the types of problems you'll see. Essentially, if you have a problem that involves a weak acid or base, and you're either asked to solve for its pH, or you're asked to solve for its K value, an ice table is most likely what you're going to need. Okay? So the big open box at the top here is set up for a reaction. So in this problem we're asked, why is the pH of water at 25 degrees Celsius equal to 7? So we're basically solving or proving why the pH of pure water at 25 degrees Celsius is 7.00. Okay? The first thing we need is a reaction. So I'm going to write the autoionization of water in the top box. Okay? Now, we've written this before, and when I've written it before, I think we use two waters as the reactants, and that's okay. Essentially, the only difference, right, is you get hydronium ions instead of hydrogen ions. But we've said, effectively, those are the exact same things. So now, we have to set up our ice table and put values in this ice table. Any value we put inside this table for either reactants or products is going to be a molarity. So, values in ice tables are molarities. Okay? All values are molarities in ice tables. So let's start filling this in. On the left-hand side, we have water. Water's our solvent, meaning that's the thing that's doing the dissolving. So we don't really have concentrations for solvents. That doesn't really make sense. And much like in the K value, the equilibrium constant expression, we don't include water in that. We won't worry about water in ice tables either. So I'm just going to put a big X below water, indicating that I really don't care what any of those things are, and in reality they're not solvable anyway. On the product side, we have our hydrogen ions, aqueous, our hydroxide ions, aqueous. We can solve for those, and that's really what we're concerned about. So the initial, okay, ice tables show us three spots in our reaction. It's like three snapshots. So the first snapshot is initial. What is going on before the reaction even starts? Well, if our reaction hasn't even started, we don't have any products. So the molarity of both hydrogen ions and hydroxide ions is 0. Okay? Then we get to change. Now our reaction is going to happen. Things are going to move. So our reactants are going to turn into products. Things on the product side are going to go up. Things on the reactant side are going to go down. But in reality, we don't know what those values are going to change by. We know we're going to get some hydrogen ions. We're going to get some hydroxide ions. But we're not quite sure what that's going to be. So we're going to use a variable. So underneath hydrogen ions for change, I'm going to put plus X. We're going to eventually solve for that X value, and that'll help us get to the pH. Now, if I'm adding X for hydrogen, what should I add for hydroxide? Well, the ratio there is 1 to 1 in the balanced reaction. So however many hydrogen ions I get, I'll get exactly the same number of hydroxide ions. So hydroxide is going to change by the exact same quantity. So it too will be plus X. We reach equilibrium. Once we've reached equilibrium, the reaction is now complete. Okay? It's done. So we take the initial, add or subtract its change, and write that in for equilibrium. So for this example, it's very simple. At equilibrium, all we have for hydrogen and hydroxide is X. So we've reached a point in this problem where we need some actual numbers. We can't solve a math problem and solve for X without some actual numbers. So we're going to use our K expression, the equilibrium constant expression. And we can set that up like we would for any reaction, products over reactants. Because this is water, we'll use KW, and essentially we get products over reactants, meaning the concentration of hydrogen ions multiplied by the concentration of hydroxide ions, all over the reactants, but the reactants are just water, which we don't include liquids into our K expressions. Now KW is a constant, so we can fill that right in. We know KW is 1.0 times 10 to the negative 14. On the other side, we have the two concentrations of the products. And we know at equilibrium, these two products are both going to have a value of X. So this value right here goes in for hydrogen ions. This value right here goes in for hydroxide ions. So in our equation, we can fill it in as X times X, or in other words, X squared. To solve for X, we take the square root of both sides. And we end up getting a value of 1.0 times 10 to the negative 7. Now, what does that mean? What did we just solve for? Well, we solved for that equilibrium molarity of both hydrogen and hydroxide ions. So in reality, that 1.0 times 10 to the negative 7 is equal to the concentration of the hydrogen ions. We're asked to solve for pH in this problem. We have an equation that can help us out. pH equals the negative log of the hydrogen ion concentration. So we can take our 1.0 times 10 to the negative 7 and plug it in. And we get a pH of 7. So this is a basic ice table using water as an example. I'm going to flip over to 2.04 and do the first problem up there. That's going to involve a weak acid. We're going to look at hydrofluoric acid and solve for its molarity. So this is the first problem on 2.04. Let's take a peek. We're going to set up an ice table. We're asked to solve for a pH of a weak acid. The way we have to do that, or the best way to approach it, is to use an ice table. So, first things first, we need a reaction. HF is hydrofluoric acid. It's weak. Okay? When we show reactions for acids, we're basically just going to dissociate them. We could include water as a reactant, but we don't have to. If you do, you're going to end up with hydronium ions instead of hydrogen ions. But I'm not going to include it in this example. I'm just going to dissociate my hydrofluoric acid into its two pieces, which are hydrogen ions and fluoride ions. Okay, I've got my reaction. Now I'm going to set up my ice table underneath. And again, ice stands for initial, change, and equilibrium. So let's think about the initial conditions of this reaction. Again, that means before anything has even occurred. So if we look at what we were given, we have a molarity of 1.08 for hydrofluoric acid. That's the initial concentration that goes underneath HF on the reactant side. On the product side, we haven't had anything occur yet, so our concentrations over there are just going to be 0 and 0. We reach the change portion. Now something's going to happen. We know our reactants are going to break apart and make products, but again, we're not quite sure how much it's going to make. So we're going to use a variable. We're going to use the variable x. Anything on the product side is going to go up by a value of x. And anything on the reactant side is going to go down by a value of x. Now, if these ratios, so that if you notice the coefficients in this balanced equation, they're all 1. If I had a coefficient of 2, it would have to go up by a factor of 2, or 2x. So be very careful. We're introing this topic, so right now everything's nice and simple, everything is 1, but don't always assume that everything will go up or go down by the same quantity. It may be different depending on the reaction and how it's balanced. Our change has been entered. Now we got to reach equilibrium. Essentially, we just combine the initial and the change to get to equilibrium. So we end up with 1.08 minus x for the hydrofluoric acid, and then x and x for the other two products. All right. So if we want to solve for x again, we need some equation or some numbers to be able to solve for it. On your sheet, you do have the Ka of hydrofluoric acid. The Ka of hydrofluoric acid is 7.2 times 10 to the negative 4. So we can set up that expression. We can set it up as products over reactants for the reaction that we used in the beginning of this problem. So Ka of hydrofluoric acid is going to be hydrogen ion concentration multiplied by the fluoride ion concentration divided by the concentration of hydrofluoric acid, HF. And now we have all these pieces to solve this expression. We have Ka. You can plug that in. We have the three values of the chemicals in our reaction at equilibrium. And we can reset up that expression and eventually solve for K. So now I have 7.2 times 10 to the negative 4th equals x times x is x squared divided by 1.08 minus x. Okay? Now if we want to solve for x at this point, it looks kind of messy because we have an x squared term, we have an x to the single power term, and we would have a numerical term. So in other words, if you're familiar with math class, you're going to probably say, well, we might need to use a quadratic equation. But we don't have to. That's a pain in the butt. We don't want to do that. So we have other tools that we can use. The first tool we can use is something called successive approximations. Okay? Essentially what this is you solve for x, ignoring the term on the denominator. So I'm going to cross off that term on the denominator. And just leave it as 1.08. Now, if I solve for x doing it this way, okay, I can take my 7.2 times 10 to the negative 4th and multiply it by 1.08. I can take the square root of that value, and I end up getting something for x equal to 0.028 with sig figs. Now, there's one of two things we can do at this point. We can take that value and see if it passes what's called the 5% test. The way we do that is we take that x, we divide it by the original concentration that we started with, and we see if it's greater than or less than 5%. If I plug this in, I get 2.6%. In other words, it passes the test. If you pass the 5% test, we don't have to do anything else. That value of x is sufficient. It works. Okay? I like to call this math magic because we essentially get rid of an x, but it's okay. It's okay that we do it if it passes that 5% rule. If it doesn't pass that 5% rule, then we have to do successive approximations. And I'll show you how to do that in a later video. So we've got our value for x now. We know that x is equal to 0.028. If we want to solve for the pH, again, don't forget that what we just solved for is hydrogen ion concentration. Okay? So all we need is the pH expression, which says pH equals the negative log of that hydrogen ion concentration. And we plug it in. If I plug the 0.028 into that expression, I end up getting a pH of 1.55. And that's how you set up a basic ice table problem.